Okay, listen up here, guys. So yesterday, we were talking about work energy theorem, okay, where the discussion we were having was that work energy theorem says that work is a change in mechanical energy and is caused anytime a force is exerted through a distance. Okay, we talked about potential energy, we talked about kinetic energy, and that's kind of where we ended off, where I was talking about how the speed of an object is exponentially related to its kinetic energy and thus exponentially related to the distance it would require to stop that object. Okay? So what we did there, believe it or not, was actually our first work energy theorem problem. Okay? Work energy theorem problems basically all work the same way. These two things are set equal to each other. Okay? The change in energy, be it potential or kinetic, okay, is going to be set equal to force times distance, or just if you're given the work, the work. Okay? And then you'll be asked to calculate something like the distance, the force, the final speed, the initial speed, the final height, or something like that. Okay? It'll just be algebra. It's just a bit of manipulation, okay? But that's the kind of thing you'll be asked to do. All right? The challenge with these kind of questions is to read the question and then determine what type of energy is being changed. Is it in fact a situation where work is being done? Okay? And then do the algebra and solve. Okay? But the trickiest part is the reading of the question and determining, is this a potential energy change or is this a kinetic energy change? Okay? If kinetic energy is changing, what's the object going to be doing?
Moving.
Okay, moving, and what else? Opposite of that. Okay, what do we call it if it's not moving at a constant rate? We say it's accelerating. Okay, either speeding up or slowing down. The energy has to change. If the object is moving, but its speed is constant, so is its kinetic energy. Okay, it doesn't require any work to keep something moving at a constant velocity. Okay, because there's no change in energy. It just has that much energy and that's what it's doing. Okay, work is only required if I want to change the energy. So for a kinetic energy change, you're going to have an object whose speed is going to change, either speed up or slow down. Okay, how do I know if it's potential energy that's changing? The example I gave to you yesterday was I performed this amazing feat of strength. And I lifted my water bottle from here to here.
If work is being done, does the potential energy?
Okay, but how do I know? If potential energy is changing, what's the object going to do? Change position, right? But change its vertical position, okay? It has to either get closer to or further from the ground, okay? It doesn't require any work for it to sit there, okay? It has potential energy there, but I'm not changing it there. I'm only changing it if I lift it or lower it. Does that make sense? Okay. All right, so that's what we're going to be looking at today, is kind of some of our first problems. But I'm going to show you a few cool examples of people doing work. Okay? And that is a guy who breaks the record for most sidewalk blocks broken with his elbow. Okay? And then some like board breaking stuff, which is kind of cool too. Okay, so mechanical energy, okay, remember, is the sum of an object's kinetic and potential energy. Anytime you do work, you're changing one or the other or both. Okay? All right, so kinetic energy, like we said, okay, the formula for that is EK equals 1/2 times the mass times speed squared. Again, that formula is on your formula sheet. You don't have to memorize it, okay? But it does still give us the units we need, which is joules. Okay, remember we learned yesterday that a joule is a kilogram meter squared per second squared. Well, when I multiply mass in kilograms by V squared, that's kilograms times meters squared per second squared. Okay, it still gives us joules. Okay. All right, ringing a bell for everybody from yesterday? The kilogram meter squared per second squared part isn't? Okay, just remember, like, this is, the reason I go over this is this. If a question ever gives you mass in grams, you need to convert it to. If it ever gives you speed in something other than meters per second, you need to convert it to meters per second. Okay, you got to get those units so that you get joules and not fractions of a joule. Okay. Okay, so that was what we did yesterday. All right, I want you guys to copy this one down. This is going to be our first example, okay, of a work energy theorem question other than the rant I had yesterday about going the right speed through the school zone. Okay, so write this one down, and then we'll walk through it together. Okay, so it's a pretty simple question in terms of the complexity of the context. Okay, so I have a rubber band that's being stretched. Okay, and someone is going to put a ball in it as they stretch it back. So it's essentially a slingshot. Okay, so is work being done in this question? Yeah. Okay, well, I know that from both the context of the question, stretching a rubber band requires a force to be exerted through a distance. Okay, and it puts elastic potential energy into the rubber band. I also know that because they give me force and distance. They outright tell me mathematically that a force is being exerted over a distance. Okay? Then they tell me I'm putting this ball in the rubber band as I stretch it, and I'm going to launch the ball using the rubber band. Okay? The question is actually about the properties of the ball. So when the ball is in the rubber band before it is released, how much energy does the ball have? Right, it has no energy. Okay, the potential energy is in the system, specifically in the rubber band. Okay, when I let go of the rubber band, the ball will gain the energy stored in the rubber band, and it will gain what kind of energy? Kinetic. Okay, so in this question then, we've identified that work is in fact being done, and that work is going to end up changing the kinetic energy of the ball. Okay? That's the first thing you have to do with any work energy theorem problem, is you have to identify, is work being done, and if so, what type of energy is being changed by that work. Okay? So our givens in this question are the distance, okay, and the force.
We have to change the distance. I have to remember.
Okay, that was what I was talking about just a minute ago. You always got to make sure your units are meters. Yeah. Okay. And it's asking, what speed would it propel the ball when released? What was the initial speed of the ball? 0. Okay. So I know acceleration is happening here. Okay. And I'm looking for the final speed of the ball. Okay. So I already wrote down that work is a change in kinetic energy. What's another way to calculate work? Force times distance. And I have those two numbers. Okay, how do I calculate change in anything? Delta always means something minus something. Final minus initial. Okay, so that would mean the final kinetic energy minus the initial kinetic energy. Now we just said the ball was initially not moving, so what's its initial kinetic energy? 0. Okay, so I can eliminate that right now. Okay, do I have a formula that calculates kinetic energy?
Yeah.
We just looked at it a minute ago. Okay, that means F times D equals 1/2 mvf squared. Okay, the formula is obviously 1/2 mv squared, but I'm putting the F in because I'm looking for the final speed. Okay, can I solve for Vf?
Yeah.
Right? Sorry, the one thing I forgot to put in the givens here was the mass, 0.125 kilograms. I have everything except Vf in this formula. Right? So how do I get Vf by itself? Rearrange the formula. Okay, so what do I do with the half and the m? Because I need to move that. Divide them over to the other side. Okay, so doesn't look at all like them. Okay, so that equals VF squared. What do I want?
VF.
I just want VF, so what do I need to do to this side? Right? If I square root VF squared, do I get VF?
Yeah.
Okay, so if I square root both sides, okay, then I get VF. Everybody okay with that? That's as tricky as the manipulation gets when you have to do a square root.
So do you have to do a square root on both sides?
Yeah, I did. I square rooted VF squared. Now I have VF, right? Okay, so now, am I ready to plug in my numbers?
Yeah.
Okay. So the force was 60 newtons times 0.85 meters divided by 1/2 times 0.125, all square rooted, should give me VF. Okay, so 60, actually I need brackets here, brackets. 60 times 0.85, okay, divided by 0.5 times 0.125. Close off all those brackets. All right, so when this thing leaves the rubber band, it should be moving at, actually we only have 2 significant digits there, so it should just be 29 meters per second. Is that fast?
Yeah.
Yeah, it is. Okay, 29 meters per second is, what's not divided times? 102 kilometers an hour, 103 kilometers an hour. I wouldn't want to be in front of that. Okay? I mean, it probably wouldn't go through you, but it would hurt. Okay, everybody follow what we did there? Here's the good news. All work energy theorem problems mechanically work like this. Okay? You're going to set work equal to the change in energy. You're going to put in all the things you know. So force times distance and 1/2 mv squared. Or if it's a potential energy question, mgh. Okay? And you're going to manipulate for what you're looking for and solve. Okay? So this part, the algebraic part, is pretty much the same for every single work energy theorem question. Right? The trickiest part is determining what's changing, potential or kinetic. That's the reading comprehension part of these types of questions. Okay? All right. Give this one a try. Same kind of question. Okay? This time you're being asked to solve for the force. Okay, let's have a look at this one. So we have a tractor that's pushing a rock, okay? And we know that the mass of that rock is 550 kilograms, okay? From rest, what does that tell me? 0. Okay, what's 0? Okay, to a speed of 4 meters per second, so that must be VF, okay, over a distance of 25 meters. What's the force exerted? Okay, so those are my givens. Is work being done? Yes. Okay, because obviously the kinetic energy of the rock is increasing, changing in some way. Okay, it's going from nothing to something else. Okay, so I identified that the work being done by the tractor is changing the kinetic energy of the rock. Okay, now they tell me in the question they want me to calculate this number. They give me this number, and kinetic energy is 1/2 mvf squared minus 1/2 mvi squared. Okay? What is vi? Okay, so what is 1/2 mvi squared? 0. Okay, so can I get rid of that? Okay. Now that's not always going to happen. Sometimes you are going to have a value there and you're going to have to do some subtraction, but that's not terrible. Okay? Can I solve for force? What do I have to do with D? Divide it over to the other side. Okay, so force is going to equal 1/2 times 550 kilograms times 4 squared divided by 25 meters. Okay? Most common mistake is people forgetting to square. Okay? So 0.5 times 550 times 16, 4 squared, okay? Divided by 550. Whoop.
Divide by 25.
Oh, wait, by 25.
176.
4,400, sorry. Divided by 25, not 550. Okay, 176 newtons. Okay, now we only have 2 significant digits, so I would have to put this number into what? Scientific notation. And I would have to round the 7 to an 8. So I would end up with 1.8 times 10 to the 2 newtons. Okay? All right. Without the scientific notation part, did everyone understand what we did before that?
Yeah.
Okay. Was it very similar to what we did in the question before?
Yeah.
Yeah, just in the question before, we were looking for V. In this question, we're looking for F. Okay? You're going to always do the same setup. Yeah, you're going to solve for F or D or V or something like that. But it's always going to be identify what kind of energy is changing, set up the math, solve. Great question.
I solved for kinetic energy, and then I did the work equals FD formula instead of doing it all together.
Yeah,
Would
fine.
it give you the same answer every time?
Yep. Absolutely. I mean, that's what I'm doing. I solved for it actually in the calculator. That's the way I did it. I solved for the top, 4,400, and then I divided by the bottom. Right? Okay. Write this one down. This one is different from the last two. Okay? Because the last two were about kinetic, this one's about potential. Okay, give you a few minutes to write that one down, then we'll walk through it. So right now, I'm hearing the whispering and I'm sensing some people are frustrated because they don't have force and they don't have. Yeah. This one's asking you to calculate the amount of work done. Are there 2 ways to calculate work? Change in energy and force times distance. Can I use force times distance for this? Well, actually, I'm going to, but I'm going to use it as part of change in energy. Okay? So I have the mass of this parcel. Okay, it's 10 kilograms. Okay, and it's on the 3rd floor of a building, 30 meters above the ground, and they're going to the 10th floor, 100 meters above the ground. So what's the height? 70 meters. Okay, or I can say the initial height is 30, and the final height is 100. It's going to come out to the same thing either way. Okay, and I also know that G is 9.81 meters per second squared. Okay, if I take this parcel up to the other floor, what kind of energy am I changing about it? It's potential. It mentions nothing about it going faster or slower. Okay, so all I'm doing is changing the potential energy of this parcel. Okay, since I don't have force and distance, I'm just going to leave W over here, but I'm going to do this. M times G times H final minus M times G times H initial. Will that calculate for me the change in the potential energy of the parcel?
Yep.
Yeah, final minus initial always calculates change. This time it's potential energy. Do I have all of those numbers? I do. Okay, so I can go 10 kilograms times 9.81 times 100 minus 10 kilograms times 9.81 times 30. And I'll have the change in energy, which is the work. Didn't need force and distance. Or, I already used force times distance. Because this is the force of gravity, and this is a vertical distance. It's still force times distance. Okay? All right. So, 10 times 9.81 times 100 minus 10 times 9.81 times 30. Whoops, I missed a 0. Okay, so this person did 6,867 joules worth of work. We only have two significant digits there, so it'd be 6.9 times 10 to the 3. But we'll just write 6867. Okay, do I always need to use force times distance? Did I use force times distance here?
Yep.
Sort of. Okay, but I mean, I wasn't given the force. Okay, I mean, I figured out the distance was 70 meters. Okay, but guys, if I'd have done this, force of gravity times distance, so that would be m times g, so 10 times 9.81 times the distance it was moved, 70 meters. Would I get the same number? Because physics, it just works. Okay? That's why we have it. If it blows up or catches on fire, it's chemistry. If it's green and smelly, it's biology. And if it just works every time, it's physics.
This would make sense.
Okay, so everyone understand why that works? Okay, when I change something's gravitational potential energy, I am working against the force of gravity. Okay, all I have to do is exert the same amount of force upwards as gravity is pulling downwards, and I can make that object move up. Okay, and so I just exert the same amount of force as gravity, m times g, then I multiply by the vertical distance or height.
Wouldn't you need to output more energy than gravity, because if you did the same as gravity, would it just not move?
It will either not move or move at a constant velocity, because I'm not changing the kinetic energy either way. So to hold something still requires me to exert the same amount of force upwards as gravity moves downwards, but it also, that moment where I accelerate it, I would have to exert a little bit more, but after that, I only have to exert the same amount as gravity in order to keep it moving. If I want to accelerate it, then I got to exert more. Okay? And we get into that in Unit 2 in Physics 20 when we talk about elevator questions in Newton's second law. Okay. Okay, see if you can do that one. This is the answer, so you can check if you did it right. Okay, I'll give you a few minutes on that one. So this one involves probably the most algebra, the most complex algebra that you would be expected to do in a work energy theorem problem, because you actually have an initial kinetic energy and a final kinetic energy in this question. Okay, so it tells us, first off, that we know the amount of work. Okay, it's 7,500 joules. We don't have to do force times distance. They told us, here's how much work is done. Okay, and we know that it is going to go from 2.0 meters per second to some unknown speed, and we know the mass is 2,500 kilograms. Okay, everybody with me so far? Okay, what kind of energy is changing about the truck? Kinetic, it's speeding up. All right, so the work is going to change the kinetic energy. Okay, so the work is going to be the kinetic energy final minus the kinetic energy initial. What I'm looking for is part of which one of those?
The first one?
First one, yeah, final. Okay, I'm looking for the final speed of the truck. That would be part of this. So what should I do with this right now? Add it over to the other side. Okay, and if you did that after you plugged in 1/2 mv squared, that's fine, doesn't matter. Okay, so the work, which is the change in energy, plus the initial kinetic energy should equal the final kinetic energy. Agreed? Like logically speaking, right? The change plus the initial should equal the final. Okay, so then that's going to mean 7,500 joules plus 1/2 mvi squared should equal 1/2 mvf squared. Everybody okay with what I've written so far?
Yep.
Okay, I'm just looking for vf, so what do I do with the half and the m?
You divide it by half and n?
Right, divide both sides by half of m. Okay, now here's a mistake some people make at this point. Ooh, there's a half m on the top and a half m on the bottom. They cancel, do they?
No.
No. Okay? Because there's an addition operation up here, they don't cancel. If this was just 1/2 of m over 1/2 of m, absolutely they would cancel. Okay? But there's an addition operation up there, so that's not true here. That solves for Vf squared. What do I want? The square root of that, Vf. Okay? Like I said, about the trickiest, most involved manipulation you're going to have to do for this. Okay? So, when I plug in my numbers, that's going to be 7,500 joules minus 1/2 times 2,500 kilograms times 2 squared. Right? There's 2. Initial velocity. Yeah. Okay? Divided by 1/2 times 2,500. Okay? That's going to give me Vf, which is going to come out to 3.16. Now, if I punch that into my calculator, this is how I would do it in my calculator. 7,500 minus, and then I go 0.5 times 2,500 times 2 squared. Hit enter, and then divide that by 0.5 times 2,500. Then I would square root. Okay, square root of 2.
It's because you subtracted.
Oh, I subtracted instead of added. Okay. So, is that making sense, everybody?
Yep.
Okay. Now, we're going to be working on this for a few days. Okay, this is like the most important concept in physics, period. Nothing happens without work energy theorem. Okay, so we're going to be spending some time on that. Hey, listening please. Need for speed labs. Due tomorrow, 8:30. Make sure yours is done. So it was all intuitive then. You're a savant when it comes to this.